In the last section, we looked at standing wave patterns formed by transverse waves. However, longitudinal waves, like sound, can also form standing wave patterns. When sound reflects from a wall, for example, the incident and reflected waves can form standing waves. Longitudinal waves on a slinky reflecting from a wall can do the same thing, as the figure indicates. As in a transverse standing wave, there are nodes and antinodes. At the nodes, the slinky coils do not vibrate at all, that is, they have no displacement. At the antinodes, the coils vibrate with maximum amplitude and thus have a maximum displacement. The red dots in the figure indicate the lack of vibration at a node and the maximum vibration at an antinode. The vibration occurs along the line of travel of the individual waves, as it is to be expected for longitudinal waves. In a standing wave of sound, at the nodes and antinodes, the molecules or atoms of the medium behave as the red dots do. Musical instruments in the wind family depend on longitudinal standing waves in producing sound. Since wind instruments, the trumpet, flute, clarinet, pipe organ, etc., are modified tubes or columns of air, it is useful to examine the standing waves that can be set up in such tubes. The figure shows two cylindrical columns of air that are open at both ends. Sound waves, originating from a tuning fork, travel up and down within each tube, since they reflect from the ends of the tubes, even though the ends are open. If the frequency f of the tuning fork matches one of the natural frequencies of the air column, the downward and upward traveling waves combine to form a standing wave, and the sound of the tuning fork becomes markedly louder. To emphasize the longitudinal nature of the standing wave patterns, the left side of each pair of drawings in the figure replaces the air in the tubes with the slinkies, on which the nodes and antinodes are indicated with red dots. As an additional aid in visualizing the standing waves, the right side of each pair of drawings shows blurred blue patterns within each tube. These patterns symbolize the amplitude of the vibrating air molecules at various locations. Wherever the pattern is widest, the amplitude of vibration is greatest, a displacement antinode, and wherever the pattern is narrowest, there is no vibration, a displacement node. To determine the natural frequencies of the air columns in the figure, notice that there is a displacement antinode at each end of the open tube because the air molecules are free to move. As in a transverse standing wave, the distance between two successive antinodes is 1/2 of a wavelength, so the length L of the tube must be an integer number n of half wavelengths. L is equal to n times 1/2 lambda sub n, or lambda sub n equals 2L over n. Using this wavelength in the relation, f sub n equals v over lambda sub n, shows that the natural frequencies f sub n of the tube are given by the following, where n is an integer. At these frequencies, large amplitude standing waves develop within the tube due to resonance, which is exactly the condition you would want in a wind instrument. Standing waves can also exist in a tube with only one end open, as the patterns in the figure show. Note that these patterns are different from those in the tube that is open at both ends. Here, the standing waves have a displacement antinode at the open end and a displacement node at the closed end, where the air molecules are not free to move. Since the distance between a node and an adjacent antinode is 1/4 of a wavelength, the length L of the tube must be an odd number of quarter wavelengths. L is equal to 1 times 1/4 lambda, and L is equal to 3 times 1/4 lambda for the two standing wave patterns in the figure. In general, then, L is equal to n times 1/4 lambda sub n, where n is any odd integer. From this result, it follows that lambda sub n is equal to 4L over n. And using the relation f sub n equals v over lambda n, the natural frequencies f sub n for a tube closed at one end can be obtained from the following. Notice that a tube open only at one end can develop standing waves only at odd-numbered harmonic frequencies, such as f1, f3, and f5, etc. In contrast, a tube open at both ends can develop standing waves at all harmonic frequencies, f1, f2, f3, etc. Moreover, the fundamental frequency f1 of a tube open only at one end is 1/2 that of a tube open at both ends. In other words, a tube open only at one end needs to be only 1/2 as long as a tube open at both ends in order to produce the same fundamental frequency. Energy is also conserved when a standing wave is produced, either on a string or in a tube of air. The energy of the standing wave is the sum of the energies of the individual waves that comprise the standing wave. Once again, interference redistributes the energy of the individual waves to create locations of greatest energy, the antinodes, and locations of no energy, the nodes.